Hello students, welcome to EPG Pathshala. I am Prima Gupta from University of Delhi, and today we are going to discuss about the module Structure of Ceramics Part 3, where we will be discussing about structure of covalent and ionic ceramics, and this is from the paper Ceramics. So students, let us see what we are going to learn in this module. So we will be learning about the structure of covalent ceramics and the basics of the formation of structures in ionic solids. Moreover, we will be discussing about the Pauling's rule for the ionic solids. So before moving further, let us clear the idea about this module. So most ceramic materials are neither purely covalently or ionically bonded materials. In the most ionically bonded materials, there is a significant level of covalency which decreases as the difference between the electronegativities of cation and anion increases. So while covalent bonding is prevalent among the group 4 solids such as diamond and many other compounds like semiconductors, most ceramics such as NaCl, that is sodium chloride, MgO, magnesium oxide, barium titanate, that is BaTiO3, iron oxide, Fe3O4, etc. are predominantly ionically bonded. So the covalent bonding, as we saw in the preceding sections, arises from the sharing of orbitals, and as a result, materials with this type of bonding are characterized by significant hybridization of orbitals and directionality of the bonds, which play a crucial role in determining the crystal structure. In contrast, ionically bonded solids are predominantly based on size difference between the cations and the anions, and the formation of structures in them is determined by a set of rules called Pauling's rule, which we will see later in this module only. So in this section, we will understand first the structure of few covalently bonded materials with emphasis on the diamond structure. Diamond cubic structure. Typical and well-known purely covalent bonded materials are carbon like diamond, silicon, germanium and silicon carbide, that is SiC. For example, in diamond, the base lattice is FCC and is built by the C atoms with half of the tetrahedral sides filled by C atoms. Thus, the unit cell of diamond contains a total of 8 atoms. The structure is typically known as diamond cubic structure. The orbital hybridization of C atoms, that is sp3, requires that the atoms are tetrahedrally coordinated, and thus the structure has high degree of directionality. One unit cell consists of 2 FCC motifs, one at 000 and another at 1/4, 1/4, 1/4. So this you can see on the figure on the right hand side. So what it means that there are 2 FCC unit cells of C intermingled into each other with origin of one at 000 and another at 1/4, 1/4, 1/4. So in case of other semiconducting compounds such as silicon carbide, zinc oxide, ZnO, zinc sulfide, ZnS, one FCC lattice can be formed by one type of atom and remaining atoms of other type occupying half of the tetrahedral sites. So in this figure, you can see the crystal structure of diamond where one can clearly observe the tetrahedrally coordinated C atoms. On the right hand side, you can see the positions of the atoms with respect to origin or the reference point. Now comes the structure of graphite. Other forms of carbon such as graphite and fullerene are also covalent bonded, but the structures are entirely different. Graphite has a layered structure where in each layer carbon atoms are sp2 hybridized and they make an hexagonal pattern. However, the bonding between the individual layers is van der Waals type of bonding. That is why graphite is a soft material and is used as a lubricant. So in this figure shown on the bottom shows that the blue part are the covalent bonding between C atom in the van der Waals forces or bonding between C atoms and between the layers. Now here comes ionic bonding. So the ionic bonding consists of large anions and small cations. Polyhedra and closed packed structures are typically formed by anions, and it is based on anions forming the base lattice and the cations occupying the interstices in them. So the rule, that is the Pauling rules, are the coordination number is determined by the radius ratio of cations to anions, that is Rc by Ra, where Rc correspond to the radius of cation and Ra correspond to radius of anions. In this rule, the maximum ligancy of minimum electrostatic energy is there. Moreover, electrical neutrality is maintained. The corner linking of polyhedra is preferred, so there is minimum cationic repulsion. The cations of high valence and small coordination number tend not to share the polyhedra elements with one another. Bond strength. The bond strength is an useful parameter to determine whether the derived structure is correct or not, at least charge neutral and stoichiometric or not. The bond strength of an ion is defined as ratio of valence of an ion to its coordination number. That is, the bond strength is given as the valence of the ion divided by coordination number of ion. In a stoichiometric and charge neutral solid, the bond strengths of cation must be equal to that of anion. Alternatively, you can work out the bond strength of an ion, and from this you can work out the valence of other ions which should match, which is needed to maintain the stoichiometry and most cases the common valence state. So, for a binary compound, that is AXBY, the coordination number of A and B are in the ratio of Y by X. Compounds based on FCC packing of ions. In these structures, typically anion from the FCC lattice and cation fill tetrahedral or octahedral sites in most cases, although in some cases some other coordination may be preferred. Here we will discuss the following structures. First is Rock-Salt structure with NaCl as parent compound. Next is fluoride and anti-fluorite structure based on CaF2 and Na2O. Next is Spinel structure based on a formula AB2O4. Now The next structure which comes in rock salt structure. The MX type compounds based on NaCl structure are under the category rock salt structure. The anions X from the cation sublattice with FCC structure. The cations M fill the octahedral sites, whereas 100% occupancy of sites according to the stoichiometry, since there will be an octahedral site per anion. Moreover, the radius ratio, that is Rc by Ra, is typical of the order of 0.147 to 0.732 with some explanations and exceptions. The examples of ceramic material such as NaCl2, NaCl, MgO, NiO, FeO, and so on. Now, let us discuss the rock salt structure with the ball model. As we have discussed in the previous slide that the lattice type is FCC and motif will be M at 000 and X at half 00. The motifs M and X are shown in this figure in yellow and green color. The 4 formula units are present per unit cell. So the bond strength of cations, for example, Na plus, is given by valence of cation divided by coordination of cation, which is equal to 1 by 6. Moreover, the valence of the anion is given as the bond strength of cation times the coordination of cation, which comes out to be 1 by 6 times 6, which is equal to 1. So first, fill all the FCC sites with X ions in case of rock salt, and then fill all the octahedral sites with the M ions. So students, you can see in this figure that 100 plane of the rock salt structure is shown in this. So you can see there are 2 types of atoms which are present, yellow and Z, which we have categorized into M and Z category. The atomic arrangement of 110 plane of rock salt structure compounds show the rows of empty rows of tetrahedral voids along the direction 001. Then we visualize the hexagonal arrays of cations and anions stacked along 111 direction, repeating in an alternative fashion. Now next come is fluorite and anti-fluorite structures. Anti-fluorite and fluorite structures. The formula for anti-fluorite structure is M2X, whereas for fluorites the formula is MX2. So some of the examples of anti-fluorides are Na2O, K2O, Li2O, and so on, whereas some of the examples for fluoride are CaF2, ZrO2, CeO2, and so on. The coordination number of anti-fluorides will be 4 for cation and 8 for anion. Whereas for fluorides, the anion is 4 and cation is 8. So the radius ratio for such anti-fluorides will be Rc by Ra, which comes out to be 0.225 to 0.414. Now let us discuss about the anti-fluorite structures. So the figure which is shown on the left hand side is the example of anti-fluorite structure where the lattice type is FCC. As discussed before, the motif X is 000 and M is 1 by 4, 1 by 4, 1 by 4 and 3 by 4, 3 by 4, 3 by 4. In this case, the tetrahedral coordination is preferred to fulfill the stoichiometry requirements. Moreover, the corner sharing of tetrahedra is there in anti-fluorite structures. Fluorite structures. So students, till now we have discussed about anti-fluorite structures. Now let us discuss about fluorite structures and their differences with anti-fluorites. So the fluorite structure is slightly bigger and has bigger cation in comparison to other structures. And the examples of fluorite structures are UO2, ZrO2, CaF2 and CO2. In practice, the coordination number of cation is 8 and that for the anion is 4. So the fluorite structure is shown on the left hand side where O atoms correspond to cations, that is M, whereas the green structures correspond to anions, that is O. So on the left hand side you can see a unit cell where cations are placed at the corners as well as the faces of the unit cell, whereas the cations are placed by FCC and all the tetrahedral voids are occupied by anions which are represented by green atom, that is O. The similar representation is shown on the right hand side, which shows the extension of this unit cell. So in this case, the motif M is 0, 0, 0 and X is minus 1 by 4, 1 by 4, 1 by 4 and 3 by 4, 3 by 4, 3 by 4. On the below right corner of the slide, you can see the view of 110 plane of fluorite structure. So in this structure, you can see that 8 primitive cubic unit cells made by anions are joined together to make a big cube and cations occupy the centers of 4 of these small cubes in an ordered fashion. So till now it is clear that fluorite structures are FCC. So let us take an example of ionic radii of a few ions. For example, U4 plus. It has the ionic radii of 0.1 nanometers. For zirconium 4 plus, it is 0.084 nanometers. And for cerium 4 plus, it is 0.097 nanometers. So the structure, as you can also see, has a large voids in the center of unit cell made by the cations. These empty spaces make such oxides good ionic conductors which are useful in various applications such as energy storage, example batteries. For having some fun with the structures, we can also draw the projection of this material which is shown on the below corner on 110 plane. Here you can see the row of empty octahedral sites along 110 direction. Zinc blend structure or fluorites structure. The zinc blend structure is of MX type compounds and they have a structure known as fluorites. So these compounds are based on mineral name of fluorites. Mostly oxides and sulfides follow this structure and some of the examples are zinc oxide, zinc sulfide and BeO, that is barium oxide, etc. Some covalent bonded materials and compounds have similar structures like gallium arsenide, silicon carbide and so on. You can also visualize diamond also having similar structures with both anion and cation being of same type. Typically, compounds with tetrahedral coordination assume this structure. In this structure, anions from FCC lattice and cations occupy the tetrahedral interstices. And this is due to the stoichiometry that half of the tetrahedra sites are filled. The compounds with radius ratio Rc by Ra of the order 0.225 to 0.414 follow this structure, with a few exceptions where bonding favors a tetrahedral coordination despite unfavorable radius ratio, especially covalently bonded compounds. Such structures followed with the covalent bonding. So students, let us see the example for zinc blende structure which is shown in this slide. So let me recall that the anions, that is X, are at the corners as well as the faces of the unit cell. So the anions are represented by yellow color, whereas the cations are represented by green color and are represented by M. So at the corners there are oxygen atoms, and at the tetrahedral sites there are zinc atoms. The coordination number for M is 4 and for X it is also 4. As you can see from this figure, the lattice type is FCC because the atoms are arranged on the faces as well as the corners of the unit cell. Moreover, the motif, that is M, has value 0, 0, 0 and X as minus 1 by 4, 1 by 4, 1 by 4. So the 4 formula units per unit cells are present. Moreover, the tetrahedra are shared at the corners in zinc blende structure. Now the last structure which we are discussing in this module is spinel structure. The spinel structure has a formula of A2 plus B3 plus whole square O4, or we call it as AB2O4. It is an FCC structure with packing of ions. The partial occupancy of both tetrahedral and octahedral sites, that is 1 by 8 of tetrahedral and 1 by 2 of the octahedral sites, are occupied. A spinel unit cell is made up of 8 FCC cells and by oxygen ions in the configuration 2 by 2 by 2. So, it is a big structure consisting of 32 oxygen atoms, 8 A atoms and 16 B atoms. This complete arrangement is shown in the figure on the right hand side. So, depending on how cations occupy different interstices, spinel structure can be normal or inverse. So, if we talk about the normal spinel structure, the chemical formula is same as AB2O4 and the examples are mainly aluminates, or we call aluminates, such as MgAl2O4, FeAl2O4 and so on. In this structure, all the A2 plus ions occupy the tetrahedral sites, whereas all the B ions occupy the octahedral sites. Now applying the bond strength rule to verify the stationary mechanics, the cations are come out to be A2 plus minus 1 by 4 into 2, and for B3 plus it is 3 by 6. Similarly, the oxygen valency will become 2 by 4 into 1 plus 3 by 6 into 3, which comes out to be 2. Now let us discuss about the inverse spinel structure. The chemical formula for the inverse spinel structure is BABO4, but can be more conveniently written as A2 plus B3 plus 2O4. Most ferrite follow this structure such as Fe3O4, CoFe2O4, etc. In this structure, 1 by 2 of the B3 plus ions occupy the tetrahedral sites and remaining 1 by 2 B3 plus and all A2 plus ions occupy the octahedral sites. Now you can hopefully make sense of the formula in the previous line. So you can see on the right hand side, the figure shows the red cubes are also contained. Moreover, it is an spinel structure with formula AB2O4. So here the blue circles correspond to oxygen atoms, the red circle correspond to B atom octahedral sites and green atom correspond to tetrahedral sites with A atoms. So students, let us summarize what we have learned in this module. So in this module, initially we have started with the structure of covalent ceramics. So in these ceramics, we have first read about diamond. So the diamond has a cubic structure which is similar to silicon carbide. So silicon carbide is SiC. Then we have read about various other structures like graphite. So graphite is also a carbon-like structure which is diamond, but it has a layered structure. Then we have moved on to the ionic solids which follow the Pauli's rule for the structure formation, which are essentially based on minimization of electrostatic energy. So in the Pauli's rule, we have discussed the condition, the ratio for the radius of cations and anions. So the ratio was the radius of the cation divided by the radius of the anion, where Rc was the radius of cation and Ra was the radius of anion. And typically anions make closed pack structure with cations occupying the interstices, such as anions are separated enough to have minimum electrostatic repulsion. So among closed pack structures, a common structure is based on cubic closed packing of anions, and here we are saying cubic because the unit cell is a cubic structure with the anions and cations present at the corners of the unit cell. So we have taken the various examples. We have read about sodium chloride, that is NaCl, zinc oxide, that is ZnO, zinc sulfide, that is ZnS, calcium fluoride, that is CaF2, magnesium aluminide, that is MgAl2O4, and then iron oxide, that is Fe3O4. So these all examples are of cubic closed packing of anions. So after this module, you will be able to understand what is closed packing, what is covalent bonding in cubic closed structures, and you should be able to understand the structure of diamond, graphite and their coordination number and alignment of atoms in a unit cell. Then you should be able to understand what is ionic bonding and what are the Pauli's rule which guide these. Thank you.